So Sean, when it comes to that point on our test, because I'm looking at it with the dot structure, electronic geometry, and molecular geometry. So yesterday you were telling us that we could just draw it instead of, and are you talking about the electric draw it or the molecular? Because if I draw it, it could look the same on both. I'm just labeling things different.
You would want to leave off your electrons for the molecular geometry. So if you were drawing it, let me pull up the exam, or the practice exam so we can.
If you want, I could ask after the break too. It's about the practice. Okay.
So do an easy one here. Yeah, let's go through this. Let me get better pens and go get the cheat sheet for everybody. Not really a cheat sheet, but the figure with all the geometries on it. And we'll go through this when we get back.
Thank you. There's 3 classes all the time. I think I keep seeing your dude at the gym.
My dude?
Your dude.
I was gonna ask you, do you train at Escobar? Maybe? Like,
Go there.
yeah, do you go there? What do they offer there? They're like open as, like, kickboxing inside? Like, is it classes? Or is it one-on-one, or you just go like punch
Probably
things?
do both. It's mostly classes, but I haven't in a few years. I saw on your social media, I used to do that.
A little, no, I would say do
You take the
it.
photos, you're fine.
Yeah.
But no, I mean, I know that there's people that are more serious about it.
Yeah.
Like practice and stuff. But a lot of times it's just class group.
So what's, how much is it?
Well, so I was one of the very first students back when I was like 14. So they gave me a kick-ass deal.
Yeah.
But I know that they just have like a lot of different
Like package, right?
exactly. So it'll be like X amount per unlimited classes for 6 months old.
Right.
Yeah. So,
Okay.
I mean, they're pretty fair about it. So.
Yeah, okay. Okay, are you talking Elements?
I do that as well.
Is that where you see my dude?
I think it's really
Uh,
just big dude mustache.
yeah, he shaved his mustache recently though.
Oh, so maybe not.
Yeah.
Dude, I saw this morning. He's got a mustache.
Oh, yeah, not him then.
But yeah.
Different dude.
Big
Yeah.
dude.
Yep. Did you still want to do a massage this weekend? Or you want to
Yes.
let me know, or?
Yes.
Okay.
If Sunday still works for you,
Mhm.
I mean, great for me.
Yeah, I'm trying to keep my schedule like this weekend, study, but, so, yeah, just, send me the time and,
Okay.
and your address.
And it is an hour and a half too long, or is that?
No, that's like my money time, like, that's like the perfect amount to get like a quality massage and actually give me time to focus on any problem areas you may have.
I got so much stuff.
Yeah, okay,
Mentally, physically, whatever.
good. Do you like deep tissue?
Yeah.
Okay.
Love it. Like, you don't mind me
Right
trying.
now.
She offered at the beginning of class, I never took her up on it, so this is, I'm ready.
I wasn't here.
Say thank you.
$1 a minute for friends and family, which is 50% off of what I really charge. And I do mobile, so I come to you. Yeah. I've been doing it for 10 years, so I'm good.
So when you get stressed out about this test, what's up?
Oh, I'm so proud. I was into the Susan so long. The last time I went was like the one by State Line, and I got there like 20 minutes late because traffic was so bad. And they're like, "You can finish your appointment, or we're still going to charge you for the whole thing." And I was like, I just started sobbing.
I would have gave you full time.
Oh.
Yeah, I don't really like working for, like, I worked for the Landing and a couple spots briefly, and I just feel like people don't get their money's worth there going into the spots. They charge a lot.
Especially if you travel.
Yeah.
Yeah, I'm sitting behind you. welcome. And again, this is just pulled straight out of the textbook. I just blew it up and printed it for you for studying purposes. Oh, sorry, I thought this was welcome. So you will not be able to use this on the test, but it's still useful to have it in front of you for study.
This stuff's gonna be on the exam?
This is going to be on the exam. Not that much, so 5 points out of 100. What's that? Okay. I don't have them with me. I can get you some more. It's totally up to you. I can print for free here, so it's just let me know and come to my office after class.
Yeah, but you only get half of the share of that. I'll do the same with, each bond has 2 electrons. So then you share only one. The double one and triple one share 8 electrons because the electrons are double.
You're in the right place then.
What's the one that right east side has enough energy to turn the electron off, which is why it has
Not just UV light. UV light actually has enough energy to break apart some sigma bonds or some pi bonds. You're trying to what?
Doesn't it mess up plants? They're out there all the time.
Because they're designed to be absorbing it. UV light.
Some of it, yes, they're absorbing it, and they're taking an electron.
But the short answer is it does to some extent, the same way that too much light gives us skin cancer, right? Plants can get the equivalent of skin cancer from being exposed to high energy radiation. It's just, it depends on what the plant is specifically. Basically, different bonds in between different atoms are going to require different amounts of energy to break the bond apart. So it says really high energy light will just straight up knock an electron off. But what's more common is if you have something like a peroxide bond, which is an oxygen-oxygen single bond attached to, I don't know, anything else. Use R as a placeholder a lot in organic chemistry. That bond, an OO sigma bond, absorbs in the low end of the UV region to the point where you can basically get each of these oxygens taking an electron, and you turn it into something where oxygen doesn't have a full valence anymore. It still has its 2 lone pairs, and it's got this unpaired electron. That's what a free radical is. Right, so basically certain bonds that when they get hit with the right wavelength of light, spontaneously disassociate and turn into free radicals. Peroxides do this, halogens do this. This is why iodine gets sold in those opaque brown bottles, because iodine will do this too under visible light. And why hydrogen peroxide is also sold in those opaque brown bottles, because visible light will make the hydrogen peroxide turn into peroxide radicals. And then they wind up going off and reacting with something else. Usually they'll steal a hydrogen from something and it'll turn into a mixture of water and hydrogen gas, small amounts. So it all comes back to it. When I said that certain wavelengths of light just straight up knock an electron off, that's not wrong, but it's more common for something like this to happen. and then you wind up with unpaired electrons that cause problems. This is most of the mutations that happen in our cells are the result of light hitting us. And either we actually take oxygen in and we turn it to CO2, right? But in the process, we actually temporarily make a peroxide bond while we're in the process of breaking the oxygen down. And if that peroxide gets let go in your cells, it can go around and cause lots of problems, which is why we have free radical scavengers, basically. They're enzymes whose job is to grab onto a peroxide or any free radical that they see and basically neutralize it, let it react some way to make it something less dangerous. Does anybody know what we call those free radical scavengers? It's a marketing term you have heard before. Superfoods are usually get touted as having lots of these. Antioxidants. Yeah, all an antioxidant is it's a piece of those scavenger enzymes that goes through and neutralizes peroxides. So you're not actually counteracting all of the damage you did to your liver by going out and drinking last night by drinking some antioxidants the next day. But you might actually be counteracting some of the damage from smoking cigarettes. Some of the damage, not all. You can't, there's not enough acai in the world to make up for smoking cigarettes regularly. But there is some science behind some of those marketing terms or those bad diets. It's just separating what's worthwhile and what's not is hard. Which is why you're in school, right? So you can tell the difference between good science and bad science. All right. So right before we left, or right after we left, there's a question about doing these problems on this part of the practice, which this is the stuff that's newest to you, so this is where I expected the first questions to come. If we have, this is going to be the way it's set up, where you have to do some Lewis dot structures, an electronic geometry, and a molecular geometry. Right, and the electronic geometry and the molecular geometry are going to be related. The electronic geometry is going to be based on your dot structure. Right, so you can just fill these in with the names if you have the names memorized. You can just draw them properly and get close to the right angles. I'm not going to get out the protractor to measure angles or make you write them on there, but you should be close. If you draw a trigonal planar like this, I'm going to mark that wrong, at least partially. Right, because trigonal planar should not be 90 and 90 and 180, right? It should be closer to 120. Right, so drawing it like this is totally fine, or you can write trigonal planar. Right, so for your dot structure, I want to see all your lone pairs. For your electron geometry, I want to see the lone pairs that are on the center atom, at least. Molecular geometry, everything should be in the same spot with no lone pairs drawn.
Isn't that tetrahedral?
It is not, because this pi bond is in the same place physically as the sigma bond, right? So both, even though it's two pairs of electrons, they only count as one electron domain. They're only taking up one spot here because they have to be in between oxygen and carbon. Right, so this still would be trigonal planar, despite the fact that there's 4 bonds. Only three of them are taking up space. What would the hybridization be on the carbon? SP. How many things have to be mixed together? SP2, right? 3 things mixed together, the S counts. Right, so 1 part S and 2 parts P gives you 3 parts total. So because that last P orbital is not mixed in, because it needs to stay back to make a pi bond between these two. And that gives you an overall different shape of being a trigonal planar instead of tetrahedral. Now, none of that will be graded on this test though. So to get back to the original question of how am I grading this section? If there's 4 questions on here, the dot structure is the most important part of each one. So out of the 4, the whole thing is 10 points. Each of these are 2.5 points, right? 1.5, half, half. Most important part is your Lewis dot structures. Actually, probably more like 1, 1, half. And so what I do when I grade these is I go through and I make the key and I assign points for every section. Even the big multi-part word problems, I'll say 4 points is laying out your roadmap. 3 points was figuring out that you needed to use density. 2 points was this. 1 was getting the final answer. Right, so I parse it out like that into these different pieces. And again, if you totally just ignored this, you could still get close to a 95 on the test. Right, this isn't that significant as far as your overall test goes. It just feels like because you just learned it, it's hard.
Can we do the dot structure for xenon fluoride?
Yes, let's do the dot structure for xenon fluoride. There's one more thing I was going to say about grading these. No, I had already forgotten it. You didn't make me forget it. I'm sure it'll come back to me, or it wasn't that important. So xenon tetrafluoride. These are also good practice problems for nomenclature other than the ions. Xenon tetrafluoride. Xenon is bringing how many valence electrons? 8. So 8 valence electrons from xenon. 4 fluorines. Each fluorine is bringing 7. Gives us a total of 36. Right, so we have 36 electrons to work with. And I'm going to go out on a limb. You guys can barely see those lines anyway. It's not going to bother you because I'm just drawing on top of these lines, right? Okay, you can still tell what I'm doing. So we know that we have to have xenon in the middle. We know we have to have 4 fluorines attached to it. How many electrons did we use? 8. So 28 electrons left. How many more does each fluorine need? Another 6, right? So 6 times 4 is going to be 24. If we fill up all the fluorines, we're going to have 4 electrons left. So let's go ahead and draw them in.
For the dot structure, do we have to circle the pairs?
No.
Okay.
Four left over. On what? The xenon is the only one that has a d orbital, right? It can't go anywhere except the xenon because fluorine has 8 electrons. And things in the second row of the periodic table, here's another one of those rare absolutes that I will give you. Things in the second row of the periodic table will never have more than 8 electrons. In fact, the fastest way you can put your OChem professor in a bad mood is to draw a carbon with 5 bonds. Right, so never, ever give more than 8 electrons to anything in the second row. So if we still have to use 4 more electrons though. So we throw them on the xenon. That's a complete Lewis dot structure. It looks really complicated and busy. And like, well, how am I going to fit all of those lone pairs into this little box that you give me? It might get a little tight for some of these. Do the best you can.
So we were only able to do that because xenon had a d orbital and we could borrow them.
Right, xenon's all the way down here, right? So even after it fills up its n equals 5 p orbital, it still has its 5d orbital that can get mixed in.
From the 4 second. Isn't that how that works?
The 4d got filled up before we got to xenon. So we're actually filling up we're using part of the empty d orbital, which is from the 5d from the next row, because that's the one that's empty.
Okay.
So then say if it was NeF4, where would those extra 4 electrons go?
There's a reason it's not any F4. That's not a stable compound,
That's not possible.
right? So you can really only really see the noble gases react to make compounds like this once you get to argon. Even argon's not pollen. But when you get down to xenon, xenon can make covalent compounds because you can wind up doing this. And if we look at the formal charge for everything here, remember that was our other way of determining whether or not our Lewis dot structure was going to be stable, right? Look at how many electrons something owns compared to where it is on the periodic table. How many electrons does this xenon control? Does it own?
8.
2 lone pairs that it owns outright, so that's 4.
Yeah.
And then 4 bonds as well, right? And it owns half of those.
So 4.
So another half of the 8 that are in bonds, 8 electrons owned. And how many does it have on the periodic table when it's neutral? 8. So xenon actually has a formal charge of 0 here, which is why this is a stable enough compound to exist. But it was one of those things that was discovered entirely by accident because somebody had like a sample vial of fluorine gas mixed with some xenon in their lab, just on a shelf, just as like a cool curiosity. Here's some fluorine gas. That's cool, isn't it? And after it sat there for about 2 years, they noticed that a white solid formed, and had no idea what that white solid was. They found the empirical formula of it, and they found out that it was 4 parts fluorine to 1 part xenon. And so that's when they first started realizing you could go past the octet rule. The octet rule is the version that only applies to the second row. That says you never go past 8 valence electrons. It's really the octet rule unless there's a d orbital.
So then just to finish out this chart, the electronic geometry, would you either say that it's, give the answer, but could you say it's an octahedral for the electronic geometry?
The electron geometry would be octahedral.
I was wondering, like, how many different kind of answers can we put in these boxes in case some of us are better at remembering, like that it's
So-
octahedral or an
So are you asking if you can take the scattergun approach and just put 5 things in there?
No, I'm just asking, like, so that way I know, like, if my brain memorizes, like I said, octahedral better than SP3 or whatever like that,
Right.
can I put, like,
Put-
how many
put-
different things can I put in there to make it right?
I've got to pick one of them.
Right.
If they don't match up with each other, like if you put SP3 but then you put octahedral, I've got to pick one of them to go from, right? So, and really you're gonna get like 3/4 credit because I'm gonna mark you down half for putting it on one of them, but then you had the other half was right. So it depends. So try to pick one way of answering it, but if you think I'm pretty sure that's octahedral, but I'm gonna draw it just to be sure. Then I would basically, if your octahedral was wrong but you drew it right, then that's a smaller deduction.
Okay.
And that would be square planar for molecular geometry.
Well, so let's finish this up and let's draw it so we can see what it looks like too.
So you can have a drawing in all 3 of them as long as they're correct.
Exactly. And it's not going to necessarily look the same because we're not trying to show perspective with the Lewis dot structure. We're just trying to show where all the lone pairs are. But then in the next 2, we don't care where all the lone pairs are unless they're on the central atom. So the answer, a graphical answer to the second column could look like
That's what you live.
so there's a drawing answer. If you wanted to draw that instead of writing octahedral
And that's for the electronic.
for the electronic geometry.
Okay.
And what would so the name, what was it, Jordan?
Square planar.
So the name for the molecular geometry is going to be square planar. And if you were drawing it, because you couldn't remember the name of square planar, you would draw it just like this, except without the lone pairs drawn.
Okay, that's my question. So you add dots if you're drawing onto the electronic geometry, but there's no dots on a molecular
Correct.
because they're already there.
Because they're taking up space, but we can't see them. That's the whole reason that they're different, is that we can't actually see these. We can
Oh,
just
yeah,
tell
you
that they're
can draw it
taking
like
up
that, I
space.
forgot. But you're still labeling everything an F or a xenon in this
Correct.
case. No, that's right. I forgot you can't
Yeah,
draw
so
it.
you're not just drawing with circles. I want you, when you're drawing your geometries, I want you to draw the element symbols.
Oh, yeah, that's right. You can't draw it by using.
So this would be a full credit answer for a xenon tetrafluoride.
Would a plus sign on the molecular geometry be wrong?
So just drawing it like this.
Yes. With the XC in the middle and the X at the
If
end.
you labeled them, that's fine,
Okay.
because that's really what we're showing here. These
Yeah.
ones, I just have it drawn as an X sticking out of the board. But if you took that and you rotated it up, you would get something that's flat and 90 degrees, right? So you could draw it like this. Just don't draw it flat when you're supposed to be showing perspective, though. Like to show the shape, if it needs to be in 3D, you better show me some wedges and dashes.
Okay, so for this one, for example, if I draw it like flat like that and then just draw the dashes and wedges on top of that with the electrons.
It gets a little bit hard if you draw this flat like that because your wedges and dashes wind up, they're supposed to be like straight out towards us, which gets kind of hard to draw. If you drew it like this,
Yeah, so that.
I probably wouldn't mark that wrong, as long as it was neat and I could tell what you were trying to say. Remember, the whole idea with these tests is you're supposed to show me what you've learned so far, right? Not trying to trip you up. It's not like there's only one right answer to some of these. Show me what you know, and if what you know is, I think it's octahedral, but I know it's this shape, then draw the shape, okay?
And then if there's no lone pairs, the drawing for the electronic geometry and the molecular geometry is the exact same.
Correct.
What about like the SP3, like that type of notation?
Yeah, you
Does
could
that work
absolutely.
For the electronic geometry and the molecular geometry?
So for the electron geometry, I'll allow that. The thing is, the hybridization does not distinguish between molecular versus electron geometry. So everything that has a tetrahedral electron geometry has the same hybridization. They're all sp3. In this case, this would be sp3d2. But you can't just write the same thing for the molecular geometry because the hybridization is the same. Hybridization is always going to be tied to electron geometry regardless of what the molecular geometry looks like. So for example, CH4, you draw it. And ammonia, NH3, they both have the same hybridization. They both have the same electron geometry too. The electron geometry for both of these is tetrahedral. The hybridization for both of these is sp3. So I want you to be more specific on the molecular geometry. You can't, if you're going to use the hybridization, that works for the electron geometry column. But then you need to either draw it or give me the name for the molecular geometry.
So the hybridization includes the lone pair.
The hybridization includes the lone pair. Anything taking up space is included in that.
Did you look at carbon tetrachloride?
Yes. So we've got 7 times 4. Sorry, 4 times 7 for the chlorines. And 1 carbon that brings 4 electrons. That gives us a total of 32 electrons, right?
I'm a mistake there, but thank you.
Counting those electrons right makes a big difference, right? Here's a clue. if you wind up with an odd number of electrons for this class, that should be a red flag. I'm not asking you about any free radicals. And so for any of these, they should always be an even number of electrons. If you got an odd number, you probably counted wrong. It's possible I made a typo on the test. That's always a possibility, but at the very least, it should be a red flag. And if you think that if you double check your counting and you still can't find where you counted wrong and you still get an odd number, come see me at the front of class and I'll either say, better check that again, or, oh yeah, I really made a mistake. I'll say, everybody look up here, turn to page 9, make this change. Like if I did something like forget the negative sign on NO2, now all of a sudden that makes it an odd number of electrons and you can't do a Lewis dot structure that's stable. And so if you wind up with something like that, it should absolutely be a red flag. But it's also a possibility that I just screwed up too. There's usually 1 or 2 places where when I'm writing the test, manage to mess up sig figs, or like sometimes when I'm writing a question, I'll not give you enough sig figs so that your answer comes out like, it looks like my number didn't change based on the number of sig figs because I have to round to 2 sig figs because of what the number you gave me is. I don't always mean to do that. So you can always come up and ask and I'll either make an adjustment or say just go with it. That's probably the most common typo I make. They don't give you enough sig figs and then you wind up with an answer that is just a 0 after you round it or something like that. All right, more questions.
Yeah, you know, since we're already on this page, why not NO2 with a -1?
Okay,
That's interesting.
it is interesting. Does it really change much though? It just changes how we count the electrons is really all.
Right.
So how many valence electrons do we have for NO2 with a negative charge?
24.
So nitrogen brings 5 electrons. Each oxygen brings 6 electrons, and there's 2 of them. And the negative charge tells you you've got 1 more electron. So just as a result of the charge. So anytime you've got something with a charge, that just means that when you're counting valence electrons, it's either going to skew it up 1 or up 2 or down 1 or down 2, depending on what the charge is. And so 18. The fact that it has a negative charge doesn't change anything else. Still do a Lewis dot structure the same way. We'll still do our molecular geometry the same way. So put nitrogen in the middle, oxygen on either side. Have to be connected, right? We just used 4 electrons, so now we're at 14 electrons left. Each oxygen needs 8 total. It still needs 6 more, right?
One needs 6 right now.
So both of them need 6, so that's going to add up, be another 12 electrons we're using.
Oh, so the nitrogen just has an extra. Okay.
So they have to go somewhere, and the nitrogen still needs another 2 pairs of electrons, right? Or 2, yeah, it still needs 2 pairs right now. We only have 1 pair to give it.
That is not math wrong.
There you go. Just in the interest of finishing this up, nitrogen's still missing 1 more pair of electrons. So what do we have to do?
Make the oxygen both double bonds.
Yeah, we add 1 more bond. We can't add extra electrons, so what we do is we make the oxygen share more.
Ah. Explain that, please.
Okay. So we were sitting right here, and everybody felt comfortable.
Well, I didn't feel comfortable there. I thought I had
It should still feel uncomfortable though, because this nitrogen only has 6 electrons, right? And we can't do that. Because
That's too many.
that's too many electrons. That's not 18 electrons anymore. Now that's 20 electrons. So we can't do that. That's why the #1 rule of Lewis dot structures is use the right number of electrons. So we also can't leave it with an incomplete valence. we need at least 8 electrons. In case of second row of the periodic table, it has to be exactly 8 electrons.
Okay.
Oxygens each have 8 electrons. They don't want to share necessarily if they already have a full valence, but if the nitrogen needs more electrons, the oxygen can take one of those lone pairs and move it over so that that is now also counting towards the nitrogens.
Because oxygen still has 8.
Oxygen still has 8. We didn't take them away from the oxygen, we just made the oxygen play fair.
No, that one, no, wait, that one would still be linear. No, we know what it.
What would it
not.
be?
It would be,
Trigonal, the electron geometry would be trigonal, and would it be flat or?
Bent.
Yeah, so it's going to be trigonal planar. So don't just leave it at trigonal, because trigonal bipyramidal is also one of our geometry names. It's trigonal planar because there's 3 things taking up space around the nitrogen. Or you can draw it. If you draw it, it should look like something like this, with a roughly 120 degrees between them.
I was gonna ask, for the electronic geometry, are we supposed to label the 120 degrees or just draw it?
If you don't think that I'm going to be able, if your drawing is really bad, and you're not sure I'm going to be able to interpret it properly, you can add the 120.
But then, like, if you messed up on that 120, you're risking.
It's a gamble. Yeah.
I'm probably just gonna mark it anyway.
If you write it down, it's got to be right, or it's going to be considered as part of your score. Right? So you can't just spew everything. You can't write down all possible hybridizations for every electron geometry and say, well, it's one of them. Right? That doesn't work. You got to show me what you know. So if you did something wrong, like label this as 90 degrees, you were most of the way there. I can give you partial credit for that. But I'm also, if you just left it like that, as long as you were close to 120 and not totally linear and not 90 degrees, I'm gonna look at that and be like, that's close enough to 120. Right? That's, in my head, that's my definition of 120 degrees, is something between 90 and 180. Good enough.
Wouldn't that one also have to be the, wouldn't you also put that in the dot structure box, but with the added,
So this is totally fine. Drawing it linear is totally fine for the Lewis dot structure. So we're not trying to show the shape. And we don't know how many electron groups are going to be, right? So this is totally fine for Lewis dot structure.
Okay.
For the geometry, I want you to show the angles better.
Oh.
Because it's a lone pair, that's not gonna look the same to molecular, but what do you put there instead?
So electron geometry would write, let's also do the written version, trigonal planar. You got to remember the planar part, because otherwise you could be talking about a pyramid or you could be talking about bipyramid. The molecular geometry would just look like that.
Yeah.
Linear?
Not quite linear.
trigonal planar.
But, you know that something goes above that envelope.
Exactly.
So how do you draw that without putting something in? That's what I don't get.
You just draw it this exact same way you draw it for the electron geometry, just leave off the lone pair. Because we're talking about when you can't see the lone pair, everything is still in the same spot, whether you can see the lone pair or not. Right, so let me pull up.
You didn't draw it for the xenon or.
Right. So, and then the name for this one would just be bent. And we do use bent for both a sp3 with 2 bonded atoms or an sp2 with 2 bonded atoms. The bond angles will be slightly different, 120 versus 109. But for the sake of giving it a name, this is bent and so is water. And just to reiterate that point before we move on to talking about something else, let's pull up that. This one we're looking for. All right, so we had, this is basically what we had, right? this is what we drew, right?
Yeah.
If you can't see the lone pairs, they're still there taking up space. So it's not like because you can't see the lone pairs, it shifts into being linear. It's still the same shape, the same bond angles for the most part even. When you're talking about the molecular geometry, we are just not going to draw the lone pairs. But they're still taking up space. And if it helps you, you can draw them on your paper and then erase them. Like draw it so that they're all 120 degrees from each other so you can see it's trigonal planar still, and then do that. Right? Because that's really what the difference is just that we can't see that, but it's still taking up the space. And that's probably the trickiest thing for most people is not when you have lone pairs, you're going across, not up and down. Once you draw your Lewis dot structure and you figure out how many electron groups you have, that electron geometry is always going to be one of this first column, and it's never going to shift up and down unless you're breaking bonds or adding new stuff. Right? So you're shifting to the side. Trigonal planar, look over one spot when there's a lone pair, and it tells you it's bent. You're not shifting up to it being linear just because you can't see it. Okay? All right. And we can keep doing practice for these, but I think we open this up to people who have questions about other parts of the test too. I think you guys are pretty strong at most of the rest of this, but if you have any particular things you wanted to discuss, Jen?
For say with something like that, on the test, are you just gonna have us grade them, or are you gonna have us grade them and explain them?
If you're 100% sure you got it right, then your explanation can be pretty bare bones. But the explanation is how I give partial credit. If you don't write an explanation and you get it wrong, I have to give you 0 because it's basically multiple choice and I can't give partial credit on multiple choice, right? So the explanation is there so that you can tell me why you ranked it that way so that if you're wrong, I can give partial credit. I didn't used to do that, but then I really felt bad giving people 0 without knowing why they ranked it the way they did. So the explain is to your benefit, especially if you think you might have got something wrong.
So like this one, the quiz you gave was really thin. Why is fluorine the largest? Because I thought it was smaller.
For ionization.
For the tiny. Yeah.
So for size, we're just looking at how many protons, how many energy levels, right? So for size, fluorine, they all have nitrogen and fluorine are both n equals 2. So same number of energy levels, but fluorine has more protons, right? It's further to the right on the periodic table. No. Because remember, the protons are in the nucleus. They don't really take up any space. More protons means it's pulling the electrons in tighter, therefore smaller. So it's harder to rank them in groups of 3 than 2. So break it up into groups of 2 and rank them. So fluorine is smaller than nitrogen. Well, we want to double check that. Nitrogen and phosphorus are in the same column on the periodic table, right? Mm-hmm. But phosphorus is in n equals 3. So bigger than nitrogen. So you've got bigger than nitrogen, smaller than nitrogen. Well, if this is smaller than nitrogen and phosphorus is bigger than nitrogen, it has to also be smaller than the phosphorus, right?
Is that an acceptable answer?
For your reasoning? Absolutely. Really cool. Yeah. It does not have to be complete sentences.
Okay.
But again,
Smaller again.
make sure that you get it. If you're getting it right, if you're sure you've got it right, then you can be pretty short on your answers. The more you're not sure if you got the right answer, the more you want to explain your logic so that I can give more partial credit.
Wait, why is, I'm just trying to figure out why I got this wrong on the quiz. Magnesium and fluorine, which one's bigger, which one's smaller, and why?
Is it magnesium and fluorine or magnesium and fluoride?
Magnesium and fluorine.
Okay,
I'm
so
looking at the quiz, not the practice exam.
yes. So magnesium and fluorine don't have the same number of energy levels, right? Which one has more energy levels? The magnesium should be bigger than fluorine. So I may have missed it your quiz when I went back to your partial credit, so we didn't talk about it. But if it's magnesium ion and fluoride with a negative charge, that's a different story, because fluoride with the negative charge has 10 electrons, and magnesium with the +2 also has 10 electrons. So in that case, they're both the same number of energy levels, and then it's all about how many protons something has. More protons should be smaller.
But it's not the same way we would solve for ionization energy, though, right?
Right, different related logic, but a little bit different. So
That might have been asking which ionization.
there was one that specifically looked at ionization energy, which is going to be a different set of logic. And the more energy levels is going to affect your ionization energy too, because the further your electrons are from the nucleus, the easier they are to rip it off.
So this has nothing to do with what we were just talking about.
No, we're going to use similar logic, but it's going to give us different answers, because this is talking about how much energy it takes to remove an electron.
And I think your B is supposed to trick us though, right? Because fluorine with a -1 and magnesium with a +2 are the exact same thing.
The exact same number of electrons. What's different about them?
Magnesium has more protons,
Magnesium has more protons.
so it'd be smaller than fluoride.
More protons, therefore smaller than fluoride. And then these two we can compare to each other because they're in the same column, right? Fluoride and chloride. Chloride has more electrons than fluoride, more energy levels too. So fluoride is smaller than chloride. The magnesium ion is smaller than fluoride. So if we're going from smallest to largest, the other thing about this is I know you're going to be in a hurry when you hit this part, but don't just do 1, 2, 3 without being careful about, wait, from smallest to largest, does that mean 1 is the smallest or is 1 the largest? Like, if you're unsure about the ranking, write smallest, or this is largest, medium, smallest. You're allowed to do that, you don't have to write it as numbers. Right? If you're unsure about is 3 the biggest or the smallest, write it out instead of just writing a number. Right? Don't make me take away the easy points. Nobody ends up happy when that happens.
We don't need to go into depth in the reasoning.
No, it can be as simple as more energy levels means bigger. More protons in the same energy level means smaller. You can just write that, and that's going to be the same logic for all of them, right? For all of the size ones?
The radius.
For all the radius ones.
Right. Ionization.
Not ionization energy. Because ionization energy is where you actually have to look at the orbitals.
Neon would have to be the highest.
So, yeah, neon's got a full energy level, right? So to break that up would be really hard. Silicon versus fluorine. Silicon looks like it's 3rd energy level, so 3p is going to look like that, right? And fluorine is 2p. Looks like that. Neither one of them is half filled. Neither one of them can get to half filled when we take away 1 electron. Right, so the half filled doesn't come into play here.
We have to add an electron.
We would want to add an electron to make fluorine stable.
You can take it away.
And we would have to we could take them away from silicon or we could add to silicon, but it's really not that close at this point, right? We'd have to add a bunch of electrons. Fluorine is going to be harder to take an electron away from because it's already so close to being stable. It's not as close as neon, which actually is stable, but it's close. It's way easier to give fluorine an electron than it is to take an electron away. And silicon's just sort of in the middle. It's not really that close to being filled. It's not really anywhere near it only being exactly halfway filled.
That makes it the lowest.
So it'd be the easiest to take this and away from. So yes, so the lowest ionization energy would be silicon, then fluorine, then neon. All right, so, and for those of you who are here and paying attention, I'll give you a little insight into how I write this question. It's 4 parts, right? 2 radius questions. And the radius doesn't have a whole lot of exceptions for the most part, right? For the radius, it's the same logic every time. There's no half-filled orbitals to worry about. For the radius part of the question, I'm going to ask you one where it's neutral atoms and one where there are ions. Same logic for both of them, nothing really tricky. When I'm looking at these for C and D, I'm going to give you one that follows the general trend and one where you really need to pay attention to the orbitals. This one, we didn't really need to pay attention to the orbitals, right?
I was gonna ask you, like, would it be okay to say in your reasoning, the trend tends to
Yeah.
decrease in IE as it goes down?
Right. And then part D, I'm going to ask you about an exception, where there's a half-filled orbital or an orbital that's where you got a full S versus P, those sawtooth P's, right? So again, if you're counting up points when you're studying and you just decide, I'm not going to spend my time on the tests really worrying about the exceptions for D here. That's 2.5 points out of the 10 here. You're cutting your losses potentially if it gives you more time to answer questions where you can earn more points than somewhere else. Right, you're totally allowed. You don't have to go into this test thinking I'm going to get 100% on every single one. Identify the stuff that's really hard for you, and then identify, is it worth it in terms of your overall number of points for you to really spend. If it's going to take you 3 hours of studying to understand this for 2.5 points, that's not worth it. I want you to come talk to me about it, and we'll talk about it. We'll get you to where you understand it, but on a testing situation especially, there's way better places for you to be spending your time in terms of grade. Okay? Now, if you understand everything else and already feel like I can get 97.5 points out of 100, this is the only one that trips me up, maybe it's worth spending some time on, see if you can get the hang of it. Or not. I was that type. I'm going to aim for a 92 and I'll know that I'm probably going to get a 90 on every test I take, and usually that's enough. That was my attitude as a student. I was not a great student though, so I'm not saying you should emulate me, but that's not a bad test-taking strategy. Know your limits, know what's good enough. Don't be a perfectionist in college, right? If you're a perfectionist in college, you're going to burn yourself out and you're going to wind up not being able to keep up with your classes because there's always more time to spend. Right? None of you are spending enough time to understand this 100% of the way right now. And that's okay, because you don't need that right now. You don't have to understand this 100% until you have to teach it. You just need it to be good enough so that you can get your A, and so that you can understand the classes that are built on it. Right?
Deep truth.
What's that?
Deep truth.
Yes. Don't be a perfectionist in college. Bad idea.
So I'm hoping I'm not the only one for D. So I get how magnesium can be pretty stable because it's already a full orbital. But which one's less stable? Like the start of an S orbital or the start of a P orbital?
The start of a p orbital would be less stable.
So the start of a,
That's that weird tooth thing.
so you've got sodium, which starts as 2 or 3, 3s.
3s1.
So 3s versus aluminum, where it's 3p1, but there's still that other 3s2 there, right? And magnesium, which is
full orbital.
3s2.
Let's write this out. So which of these is going to be easiest to take an electron away from? Well, we know it's not going to be magnesium, right?
Mhm.
Because magnesium only has full orbitals. Yeah, it's an s orbital, but it's still full. That's still better than partially filled.
Which makes it the highest.
Which would be the highest ionization energy. It's the hardest to take something away from. Out of these, part of it is you have to look at what you're going to make. They both have one electron by itself in an orbital. But in the case of aluminum, if you take that away, you still don't have only complete energy levels, right? You still have an n equals 3, this s orbital by it, or this s orbital that's filled, but it's still better to only have completed energy levels, right? Versus if you took this one away, now you're back down, your valence is now 2, and your n equals 2 is totally filled. You went to having only exactly filled energy levels by doing this. So that's really easy to do. This one is easier than breaking up a full orbital, but it's not as easy as sodium. Sodium is going to be the easiest because it's so close to being stable. All it has to do is give away 1 electron and it's there. Aluminum has to give away 3 to be really stable.
So
It gets better by doing this. Yeah, the easiest is the lowest ionization energy.
Okay.
It takes the least energy to change it. All right, so, and again,
If
you're
we drew
answering
that
this.
in our explanation, does that count as
That's
well?
perfect. That's a great way to explain it. So lowest, I would not even do 1, 2, 3. It just makes it tricky. You're putting yourself in a tricky situation where it's easy to misunderstand for no reason. So lowest, maybe I'd do that if I'm lazy. No, it'd be, or lowest, highest, and 2, or mid, or whatever you want to write. Give me something so I know that you considered it, but this would be the way it takes a few more letters than just writing 1, 2, 3, but less likely for you to screw up on your numbering.
Real easy, hardest. Like to go away the electron, would that be incorrect? I just won't.
I want you to put it in terms of, just don't. It's not the wrong way to understand it, but we don't rank energies in terms of easiest. We rank energies in terms of highest and lowest. So it's just the wrong term for it.
I love how she took your silence as an answer.
Well, not really the wrong term.
I'm always willing to
Yeah,
consider
Just the wrong perspective.
consider it, and
Yeah,
you know, is it just that I have this preconceived idea that it should be highest and lowest, or is there a reason for it? And I think there's a reason for it in this case.
We were like easiest.
You wrote easiest to take.
Electron, part of it like that, were they reasoning?
That could be part of your reasoning.
Okay. This is how I figured it out, so I'm worried if I
Yeah.
did it that way.
You'll at least get most of the points if you did that. All right, we're coming up on the end of the class. I have office hours after this though, and there's no class in here, I don't think, afterwards. So I'm willing to hang out in here and keep answering questions here, or we can go down and by the bio lab or in the chem lab, keep working on this if anybody has more questions you want to go over.
The test, can I just get that from Canvas?
It's on Canvas as a PDF. If you want a printed copy, follow me down to my office and we can print off copies for anybody who needs a paper copy. Okay? And don't turn it in to me on paper until you take the test. I want you to have it. If you want to turn it in, get it off your plate, turn it in digitally. I won't take any paper copies until the day of the test because you're supposed to study from it. The practice test.
Yes, you Sean.
No problem. Anybody who has to get to another class really quick after this, but I'm going to ask a question we didn't get to. We still have 5 more minutes.
The test is on Tuesday at 1.
Tuesday at 1, right here.
You said you don't have lab on Tuesday?
We'll meet there is another assignment, but you have all week to work on it, so you don't have to work on that assignment. I'll give you the assignment and you can start working on it, but then you can use the rest of the time to get your final questions answered or review for the test, that kind of thing.
Oh, okay, so,
So I will be here.
You'll
You,
be
you
here
do
as
not
well,
need
okay.
to be there.
okay. Gotcha.
I have one question.
Yeah.
I think you know I do. I'm a little bit confused about the rules